Hello, students, and welcome to our lesson on solving literal equations. This is arguably our most mathematical lesson in this course, and I personally find it to be the most fun because instead of getting ugly numbers potentially, where you have to deal with fractions, decimals, things you really don't want to look at, almost everything we're about to do is just going to be with variables. So let's get right into it. What is a literal equation? So a literal equation is otherwise known as a formula, and literal equations or formulas are equations that relate two or more variables. So later, we might introduce what are called functions, where we can find one variable's value using a function that'll turn one variable into another variable. But for right now, we just call them formulas, where we don't need a graph or anything. All we have to do is isolate or solve for a specific variable. So for instance, we have a equals pi r squared. This is a formula you should recognize. This gives us the area of a circle based on its radius r. So if you take the radius and you square it and then multiply by pi, that gives you the area of that circle. So we have some terminology that goes along with this. This is a formula relating the area of a circle, which is the a variable, to its radius, which is the r variable. In the state we wrote it in right there, we would say that it is solved for A, or that it is written in terms of R. So now let's break down that wording. Solved for A because A is all by itself on the left side of the equal sign. So just like in past lessons, we solve for X in a lot of problems, here we solve for A, meaning we get A all by itself. But we say that it's written in terms of R because the terms of this formula have r as their variable. So you solve for a and you write a in terms of r. In the current state that we have that equation, we would say that if we know r, then this formula is ideal. So we can make a little note here that this is ideal for finding area if you have the radius. So if you already have the radius, you can just plug the radius into this formula and solve for the area very easily. Because, for instance, if the radius is 2, I just plug in 2 for r, I do 2 squared and multiply by pi, and I'd get that the area is 4 pi. But if I have the area and I want to know what the radius is, this formula is not all that helpful because I would have to plug in a and then divide by pi and then square root both sides just to get the r value. And imagine you have to find multiple r values based off of multiple areas. You don't want to do all those steps over and over again. So instead, what we do is we solve the literal equation for the variable that we want to find. So the same equation, a equals pi r squared, can be rewritten as r equals the square root of a over pi, where in order to get r by itself, we divide both sides by pi and then we square root both sides. We would say that this formula is the same formula, but now it is solved for r, and we would say that it's written in terms of a. Because r is isolated, so we solved for r, but the equation itself has terms that use the letter a, or the variable a, in them. So in this state, we would say that this is ideal if you have area and you want radius. So if we already know what the area is, but we want to figure out what the radius is, it's convenient to have the radius as the isolated variable and a as the terms in our expression. All right, so now the whole point of this lesson is to get across that we can solve literal equations for really any variable that is in the equation. And so generally speaking, we would say that we can solve literal equations for specific variables to fit the needs of different scenarios. So the key there is we want to fit the needs of whatever we're doing. If I need a solve for area, I want to use a formula that has area isolated. But if I want to solve for radius, I want to use a formula that has radius isolated. All right, so now steps for solving literal equations. Solving a literal equation for a specific variable requires getting that variable alone, also known as being isolated. Okay, just like we were getting variables alone or isolated in previous topics. To do so, we're going to use the exact same process and inverse operations that we would use to solve linear equations. So, for instance, if we have 3x plus 1 equals 10, if we want to get x isolated, we would subtract 1 from both sides. Let me do that in red. We would subtract 1 from both sides. Then our minus 1 and our plus 1 would cancel each other out since they're inverses. We would get 3x equals 9. And then we would divide both sides by 3 to get that x is equal to 3 because these 3's would cancel. We can do that exact same thing without ever actually knowing what the numbers in the problem are. So this original problem up here looked like a number times x plus another number equals another number. We can represent that, generally speaking, as ax plus b equals c, where we have a number times x plus another number equals a different number. So we're going to solve using the exact same steps. We're going to subtract b from both sides, and we're going to get that ax, the b's cancel each other out, so ax is equal to, and on the other side, because we don't actually know what c minus b is, we just write c minus b. As of right now, those are not like terms, so we can't put them together in any way. We just leave them general, c minus b. But then I want to get x by itself, so I can now divide both sides by a, where notice when I divide both sides by a, I write the entire right side over a. So I draw this line all the way across. Every individual thing is divided by a. On the left, these a's cancel, so I just get x. And on the right side, we leave it nice and general like that, c minus b over a. So if we look at the original problem we had, where we had an a value of 3, a b value of 1, and a c value of 10, if we take those a, b, and c values, we would have c minus b is 10 minus 1, that's 9, and a was 3, so we would have 9 over 3, which is 3, the exact same thing we got here. So if we want to solve for x all the time, and all our equations are going to be in the same format, I don't have to solve with all the numbers plugged in. I can solve generally and then plug the numbers in after. So we want to do whichever one fits our needs better. All right, so now let's solve for some other things. We have number 1 here, solve for r. R is going to represent radius. This formula says c is equal to 2 pi r. This is the formula for the circumference of a circle based on its radius. Right now, we would say that this formula is solved for c, and it's written in terms of r. What we want to do is isolate r. The way we do that in this case is we divide by the things next to r. So by next to, in this case, I mean that this 2 pi right here is being multiplied by r. Even though pi might look like a variable, pi is just a number. And so 2 pi is really just a number itself. So 2 pi is the coefficient of r. And just like we did with the 3 right here up above, whatever the coefficient of x was, we divided by it to cancel out on that left side. So here we divide by 2 pi because that will isolate our r variable by making the coefficient of r equal to 1. So I just get 1r on the right, and on the left side, c over 2 pi is as simple as we can make it. There's nothing else we can do to that. And so c over 2 pi equals r is our final answer. We have now solved this equation for r, and we've written r in terms of c. All right, we're going to do the same thing for number 2. We have d equals rt. We want to isolate t. So r in this case is the coefficient of t. So we're going to divide both sides by that coefficient. On the right side, r and t cancel each other out, or sorry, r and r cancel each other out. We're left with d over r on the left is equal to t. So now, why did that work? When we divide RT by R over here on the right side, we're really getting an equivalent fraction. So RT over R, we can think of these R and T as factors. So when you have factors such as, when we had 9 over 3 a second ago, we could rewrite that as 3 times 3 over 3 and cancel out one of those 3's. So when we do 9 over 3 and we get 3 as our answer, it's because 3 is that remaining factor on top. In this case, we have r times t over r. So in the same way I crossed off the 3's above, I can cross off an r from this part. So really, we're just dividing by r to get a 1 there, but you can think of it as factors canceling, just like when we reduce fractions. We would now say that this formula over here is solved for t, and it is written in terms of d and r. We would say that this is written in terms of d and r because we have two variables over there, the variable d and the variable r. In the first problem, we said it was written in terms of c because c was the only variable on that left side. Okay, some more examples here. In number 3, we want to solve for h. We have a equals 1/2 base times height, or 1/2 bh. Sorry, I instinctually thought of a triangle when I was reading this. And so if we want to solve for h here, we have two things that we have to move to the side. Because right now, h is being multiplied by both 1/2 and by b. So even though we could do it in one step, I'm going to go ahead and do 2 steps to get h by itself. So I'm going to multiply both sides of this equation by 2, because 2 is the reciprocal of 1/2. So when I multiply by 2, it's going to cancel out this 1/2 in front, because 1/2 times 2 is just 1. So I'm going to get 2a is equal to bh. Now, I have h and b multiplied together, so in order to get rid of that b, I'm just going to divide by it on both sides. By dividing by b, on the right side, these b's cancel each other out because they divide to give us 1. b over b just equals 1. And so we're left with 2a over b is equal to h. So we have now solved this formula for h, and we would say that h is written in terms of a and b. All right, for number 4, we want to solve for w. We have p equals 2l plus 2w. This is the formula for perimeter of a rectangle, where you would multiply 2 times the length and 2 times the width and then add them together. So if we want to solve for the width, imagine we already know what the perimeter and the length are, then we can isolate w in this equation, and then we'd be able to plug in those two values. So to get 2w by itself, we want to move the 2l to the other side. So I will subtract 2l from both sides. On the left, we can't combine p and 2l because they're not like terms. They have different variables. So I have to write them next to each other as p minus 2l. On the right side, we subtracted the 2l that was over there, so it goes away, and we just have 2w left. Now I want to isolate the w, so what I can do is divide both sides by the coefficient of w, which is that 2, and we're going to get that p minus 2l over 2 is equal to w. This is a perfectly acceptable format for this answer, where we have that w, which would represent the width of a rectangle, is equal to the perimeter minus 2 times the length divided by 2. Nothing wrong with this. However, we could write it in a different format if we wanted to, where we can split this fraction on the left into 2 fractions. So I can write it as p divided by 2 minus 2l divided by 2 equals w. And by doing that, I can now cancel out one of these 2's, or the 2's that are attached to the w fraction. And this will simplify to be p over 2 minus 1l, or just l, is equal to w. This is not necessarily better, but in some ways it does look cleaner. So to be honest with you, any of these are actually fine. And I'm going to even go one step further. If I put this on the side here, okay, that current answer is perfectly fine, but we can even write it another way. We could say instead of p over 2 minus l, we could say 1/2 p minus l equals w. and these are all acceptable. So whether you write the one on the left over here, or you write either of these two, okay, these are all acceptable because depending on your format, one might be preferred over the other. But in our case, they all represent W being solved for, they all represent a formula for W that is written in terms of P and L. So all of these over here are acceptable. All right, number 5, we want to isolate X. So now what we're really doing here is we have a linear equation, 3x plus 2y equals 10. Usually we solve for y in these equations because we want y equals mx plus b form, which is slope-intercept form. But that doesn't mean we have to solve for y. Okay, we always have the option of solving for whatever variable suits our needs. So in this case, we're going to be solving for x. So what we're going to do is move everything without an x in it to the other side. So in this case, we will subtract 2y from both sides. And when I do that, I just want to make sure that I don't accidentally combine things that can't be combined. So on the left, the 2y's cancel each other out. But on the right side, I have to be careful. 10 minus 2y does not become 8y. Okay, we can't do the 10 minus 2 there, so we just have to write them separately. 10 minus 2y. Always remember, whenever you do not have like terms, you have to leave terms separate. All right, now we want to get the x isolated, so we want to make the coefficient a 1. So I divide both sides by 3. Where notice again on the right side, I divide the whole thing by 3, not just the 10 or not just the 2, but the entire side by 3. And this is going to give me that x is equal to 10 minus 2y all over 3. This is a perfectly acceptable answer. We could also go one step further though, just like we did in the last problem, and write this as x equals 10 over 3 minus 2 over 3y. I would argue though that this is actually a worse answer. So I would prefer that you leave it as one fraction, but there are times when this is better. So notice in question number 4, when we divided, or when we split it into two fractions, we had up here that we had 2L over 2, so this simplified to just be L. In that case, it's better, I would argue, to write it as P over 2 minus L, because we don't like when we have common denominators, or common factors in numerator and denominator, I should say. So over here in number 5, we don't have that same case. Nothing cancels out particularly nicely in this when we go to this other form, and so I would argue that the top form is the better one. All right, now there's a you try. So if you haven't taken a chance to pause the video yet, please give this one a chance. Hopefully you paused the video. So now we are going to solve for y. This is a very common thing we do, is take a linear equation and solve for y. Essentially, we are putting this line into slope-intercept form. So in order to do that, we need to get everything without a y in it to the other side. So we're going to subtract 4x from both sides. When we do that, on the left side, the 4x's cancel, and we're left with negative 3y is equal to, and be careful again, we cannot combine the 12 and the negative 4x, so we just write them next to each other, 12 minus 4x. Now we're going to divide everything by a negative 3, where again, I put the entire right side over negative 3, not just one of the things, but everything. On the left, the negative 3's divide each other out, so we just get 1y. And on the right side, we could technically write it as 12 minus 4x over negative 3, but this is not ideal. Okay, we do not prefer this form because we have a negative sign in the denominator. So we have two options of what we can do here. We can either split it into two fractions, like we were doing in the previous problem, so like what we did over here, or we can just move that negative sign to the numerator by rewriting it as a negative up top. So two options. We can either rewrite it as y equals 12 over negative 3 minus 4x over negative 3, and then simplify this to be y equals negative 4 plus 4 over 3x, where this became a positive because we had two negative signs above it. So that's one option. Or we can leave it as one fraction but move the negative sign to the top, where we would get y equals negative 12 plus 4x all over 3. And this one is better because we no longer have a negative sign in the denominator. So as you answer these questions, it is technically not wrong to leave your answer in this format up here. But the format that I at least would prefer is this one right here, where we took that negative sign and moved it to the top. And when I move that negative sign to the top, we just have to make sure that we distribute this negative sign to both things on top. Because what I technically did to get there is I multiplied everything by -1. So top and bottom, I multiply by -1, where on bottom, that gives me a positive 3. And on top, I distribute the -1 to get negative 12 plus 4x. All right, so either method there is okay, but the method on the right is preferred in this case because, again, when we split it into two fractions over here on the left, it doesn't actually simplify to be anything nice. So it's better usually to leave it as one fraction if it's not going to simplify. All right, now we got a harder one. Number 6, we want to solve for x, but x is a little bit hard to get to in this case. So whenever you have x in a hard to get to position, usually you want to kind of break it out of its shell before you try to isolate it. So what we're going to do first is distribute this -1/4 to the w and the negative x. That's going to give us -1/4 w plus 1/4 x. And I still have the rest of the problem in front of it. Okay, I end up with positive 1/4 x because I had a negative times a negative gave me a positive there. So now we want to get everything that does not have an x in it to one side. So I'm going to subtract 27 from both sides. So minus 27 on both sides. Where I have to be careful on the left, y minus 27 stays separate from each other. They do not combine. On the right, the 27s cancel. And I'm left with -1/4 w plus 1/4 x. Now I'm going to move the 1/4 w over. So I'm going to add 1/4 w to both sides since it's a -1/4 w. And again, when I write this on the left side, I just have to be careful over here. Oop, I wrote an x over there actually. It should be a w, -1/4 w. So now on this left side, I have to be careful. I have a y term, a constant term, and a w term. They do not combine. They are all different variables, so I have to leave them separate from each other. So I'm going to have y minus 27 plus 1/4 w all separate. And on the right side, these 1/4 w's cancel. I just have 1/4 x. Very important we leave variables separate when they are not like terms. So now last step, we have 1/4 x. So I'm going to multiply both sides of this equation by 4 because 4 is the reciprocal of 1. So when you want to get a variable by itself and it has a fraction as a coefficient, we multiply by the reciprocal. On the right side, we have to distribute that 4. So we get 4y minus 27 times 4 is 108. And then 4 times 1/4 w is just w. On the right side, 1/4 times 4, those cancel to just give us x. And so all in all, we end up with x is equal to 4y minus 108 plus w. And we could write this in a different order technically, but there's no real reason to. Having it as y, a constant w, perfectly acceptable. If you were going to rewrite it, you would put it in descending order, and we would do it with alphabetical, what do you call it? An alphabetical sequence. There you go. Where the alphabet goes W, X, Y, and Z. So we would write the W, then the Y, then the constant in the back. But this format, perfectly acceptable here. All right, last one, number 7. We want to solve for x. Remember in our last topic, we talked about proportions and how cross products are equal. So here, if we want to get x by itself, we can start by finding the cross products, which give us b times x equals, and the other cross product is a times c. Then to get x by itself, we just have to divide by that b term. So if I divide both sides by b, the b's on the left will cancel, and I'm going to end up with x is equal to ac over b, where we now have x written in terms of a, c, and b. In the previous problem, we had x written in terms of y and w, and we can say this for all of these equations. We can isolate one variable, say that we solved for that variable, and then say it's written in terms of whatever variables are on the other side. So just a note on this last one here, as a reminder from proportions, we cross multiply in order to get those fractions cleared. All right, guys, that's all I have for you in this one. Hopefully you enjoyed solving literal equations.